Good morning to all. In this video, I'm going to explain about the overview of the first unit in the subject Digital Principles and System Design, and the subject code is 22 EC 101. Unit 1, Boolean Algebra on Logic Gates. In this unit, we are going to see the review of number systems, its representation and conversions, review of Boolean algebra, theorems, sum of product and product of sum, simplification, canonical forms, min term and max terms, simplification of Boolean expressions, Karnaugh map, implementation of Boolean expressions using logic gates and universal gates. Number system. Number system, that is, system of naming or representing the numbers. There are various types of number systems. The first one is binary number system. Its basis or radix is 2. Decimal number system, its base is 2, that is base or radix is 10. Octal number system, its base is 8 and it uses the numbers of 0 to 7. Hexadecimal number system, its base is 16, that is the digits used is 0 to 9 and the letters used are A to F. Then we are going to see about the number system conversions. We can convert the number system, each number system to other number system. That means, for example, we can convert the decimal to binary or binary to decimal or octal to decimal and octal to binary like that. So the first one we are going to see is the decimal to other base system. That is decimal to binary, decimal to octal, decimal to hexadecimal. The first conversion is decimal to binary. Say for example, convert 108.188 to the base 10 into its binary. That means, so first of all, convert the whole number 108, okay, to the binary system, and then convert the decimal point, that is 0.188 into, multiply with the 2, and you multiply each number with the 2 to 4 or 5 times. Then, so according to the arrow mark, we have to take the answer. So this is the conversion of decimal to binary. The next one is decimal to octal. Similarly, octal is a base 8. So therefore, we have to divide it by 8, and also for whole number and also for the decimal number, we have to multiply by 8 and we have to write down the answer. Then the next one is decimal to hexadecimal. Hexadecimal means 16. Therefore, so divide the whole number with the 16 and multiply the decimal point with a 16 and write down the answer. And the next type of conversion is a binary to other base system. The first one we are going to see is the binary to decimal conversion. So the whole part of the binary, so multiply with the 2 power 0, 2 power 1, 2 power 2, 2 power 3, etc. And the decimal values of this binary, we have to multiply with the 2 power minus 1, 2 power minus 2, 2 power minus 3 and so on. And then finally write down the answer. That is the conversion of binary to decimal. Then the next one is the binary to octal. That means binary to octal means make a group of 3. Okay, make a group of 3 and you have to write down the answer. Then the next one is binary to hexadecimal. Binary to hexadecimal means make a group of 4. So make a group of 4 and we need to write down the answer. That is the binary to hexadecimal. The next type of conversion is the octal to other base system. So conversion from octal to other base system, that is the first one is octal to decimal conversion. So first convert the decimal octal number into decimal number. That is, multiply with that of the 8 power 1 or 8 power 2, 8 power 3, that's it. Then they convert octal to binary conversion. So that means, so for each octal number, convert that into corresponding binary numbers. Then the next one is octal to hexadecimal conversion. That means first convert the octal to decimal, then decimal to hexadecimal. That means first convert this octal to its binary number. First convert the octal to binary number and then binary to hexadecimal. So there is a two-step conversion. Then the next one is hexadecimal to other base system. So hexadecimal to decimal, so multiply with the 16 power 0, 16 power 1, etc. for the whole part, and for the decimal part multiply with 16 power minus 1, 16 power minus 2, etc. and write down the answer. The next one is the hexadecimal to binary. That means, so each hexadecimal value convert that into binary. Next one, hexadecimal to octal conversion. So first convert the hexadecimal into binary and then the binary to octal. That is called as hexadecimal to octal conversion. Then the topic is ones and twos complement. So the ones complement of a binary number is defined as the value obtained by inverting all the bits. If you invert all the bits, then that is nothing but the ones complement. And if you, after inverting, if you add 1 in the LSB, then that is called as the twos complement. So this one is an example for a twos complement. Then the next one is Boolean algebra, theorems and properties of Boolean algebra. Here are some of the theorems of Boolean algebra. Some of the properties of Boolean algebra. Then canonical and standard forms. So here there are two form of expressions, that is SOP and POS. That means sum of product terms and product of sum terms. So in this tabular column, here is a representation of min terms and as well as the max terms. Min terms is nothing but the sum of product terms and max terms is nothing but the product of sum terms. Let us have some of the examples of a canonical SOP form and as well as the canonical POS form. Then the next one is the Karnaugh map. So in Karnaugh map, why we are going for Karnaugh map is, in order to minimize a Boolean expression, the K-map reduces the logic functions more quickly and easily compared to the Boolean algebra. There are many types of K-map. So 2 variable K-map is there, 3 variable K-map is there and 4 variable K-map is there. Let us have an example for the 4 variable K-map. So here the minterms are given. So in this minterms, just represent 1 in each minterms and finally group it and then write the Boolean expression. Here in this problem, we are having 3 groupings. One is nothing but the octal grouping and the 2 quad grouping. So how to do the K-map, how to do this problem is, that is for the given minterms. So first write 1 in that minterms and then make a group of highest number of grouping. Okay, and then finally write the Boolean expression. So this is the procedure to follow the K-map. Then last and final topic is a logic gates. There are AND gate, there is a product of 2 inputs, OR gate, there is sum of 2 inputs, there is NOR gate, inverting, NAND is nothing but the complement of the AND gate, and then NOR gate is nothing but the complement of the OR gate, then XOR gate and the XNOR gate. Universal gate. The NAND and NOR gate are called as the universal gate because we can fabricate by using AND, OR and NOT. These are the simple diagrams of NAND gate as a universal gate by using simple AND, OR and NOT functions. NOR gate as a universal gate by using simple AND, OR and NOT functions. So this is an example of a function using NOR gate. So these are the steps. That is, the first step is draw the logic diagram, that is AOI logic diagram, add bubble to the output of the OR gate and add bubble to the input of the AND gate, do bubble compensation, then finally represent all gates as a standard NOR gate. So this is the steps to follow by implementation of the NOR gate. Then this is an example for the implementation using NAND gate. So the same procedure we have to follow. First draw the AOI logic diagram and add bubble to the output of the AND gate and add bubble to the input of the OR gate and do bubble compensation and finally represent all gates in the NAND. So these are the steps to follow the Boolean expression using NAND gates. Thank you for watching this video.